Our next speaker is Sergio Uribe from Chile. Sergio was just recently promoted to full professor at his university. Congratulations.
Thank you very much.
The title of the talk is State of the Art and Recent Advances in Quantitative Flow Imaging.
So thank you very much for the introduction and also for the invitation to give this talk. So I will talk about flow quantification, and first I will briefly summarize the standard method that we can obtain for flow. Then I will talk about some bank issues and some unwrapping methods, and then I will move on to talk about for the flow and the quantification of for the flow data. And at the end of my presentation, I would like to just talk a little bit about the application of AI for the flow imaging. So let's start very easy. In a standard 2D flow, if we draw a region of interest in the aorta, for instance, we can then multiply the area by the mean velocity, and we obtain this flow curve. And as Tekla mentioned, the positive area means the forward flow, and the negative area means the retrograde flow. And from that method, you can obtain the net flow by subtracting the retrograde flow from the forward flow, and you can also obtain the regurgitation fraction by dividing the retrograde flow by the forward flow. So I believe this approach is very well known by most of the people here in the audience, and although this method is very standard, we still suffer from some issues, or at least with one issue, which is how to set up the bank properly. So if bank is set too low, we get some velocity aliasings, but on the other hand, if we get bank too high, we get some images with low velocity to noise ratio. So some researchers have been working on how to obtain unwrapped velocity data with high VNR. So over the last years, different dual bank approaches have been proposed. And in dual bank, we obtained two different sets of phase contrast images, one with a high velocity encoding data and another one with a low velocity encoding data. And different methods have been proposed to use this data to unwrap the flow data. So like the standard dual bank approach, the biconditional and the three-conditional unwrapping method, and also the optimal dual bank data. And in most of the cases, the high velocity encode data is used to unwrap the low bank, basically. Another approach that I would like to highlight is the paper published by Locker et al. In 2016, in which they used the Laplace operator to unwrap the data at different scenarios, as you can see in this figure, but without the need of having two bank data sets. So let's move now to 4D flow, and I believe also that most of the people here are very familiar with this technique. So in 4D flow, we can obtain the velocity in a 3D volumes along three orthogonal directions along the cardiac cycle. And 4D flow can then be used to visualize the flow patterns. And I remember that back in 2005, 2007, most of the people were very impressed with these similar videos at different conferences, and I think we still are. But the discussion at that time was how we can obtain quantitative data from these pretty pictures. So some researchers start working on quantification of 4D flow data, and one of the first papers came out in 2008, where Stadler and co-authors put this fantastic paper describing how to obtain wall shear stress from 4D flow data. Then in 2010, one came up with a paper describing how we can quantify vorticity in the cardiac chambers. And in 2014, also Lawrence developed a method to quantify elasticity in the aorta. And although those techniques were perfect and are very, very nice, there was something not right, because we were kind of quantifying just a few slices over the aorta, for instance. So we were doing a 2D quantification over the 4D flow data. So we weren't taking advantage of the 3D velocity field that we have at that time. So some researchers started to develop some 3D quantification now of the aorta, for instance, taking the advantage of the 3D full field velocity, and many parameters started to show up, like not just the wall shear stress, but also the eccentricity, vorticity, turbulent kinetic energy, just to mention a few of them. And the nice thing about all these parameters is that they can be described with a relatively easy mathematical formula. And our group actually in Chile has been very active in this research, and we propose actually a library for quantifying for the flow using this 3D approach, using just a single segmentation from the aorta, for instance. And our approach is that you can take the segmentation, you create a theta error mesh, and then you interpolate the velocity field into the nodes of the mesh, and then you calculate all these 3D parameters just from a single segmentation. Also, a nice thing about our method that we can calculate this Laplace equation in the aorta, which allow us to project any 3D vector quantity into the normal, radial, or circumferential coordinates, so that we don't only obtain the world shear stress magnitude, but we can also obtain the world shear stress, the axial, and the circumferential component. So people was very excited about this 3D quantification, but as Tekla said, we have still some issues in order to put all these parameters into the clinic. And I think one of the main limitations is standardization. So many vendors have different DICOM formats, and each group, of course, they analyze the data with their own methods, and sometimes it's difficult to compare the results from different centers. And as also Tekla said, there is still a single easy tool to quantify all these 3D parameters, and there are not also many softwares available. But likely, some of the companies have already, and actually the same conclusion came out in one of the first consensus statements for the flow paper, and they say that visualization and flow quantification is being performed using in-house developed tools, so I have to read that, and the field, they say, would benefit from greater standardization in data analysis, methods, workflow, and data output format, which in turn affect the use of analysis tool. So likely, some of the companies have already taken some of these methods into the software, and we have also developed an application, a toolbox in MATLAB, so that we can actually calculate some of these 3D parameters. And if you want to use the software, you can just drop me an email, and we can send you a link so you can download this tool. So the last part of my presentation, I would like to talk a little bit about the application of AI and for the flow. And as you can see in these slides, there have been already some research about the application of AI and for the flow. And I don't have much time to go into details of any of them, but as you can see here, there are some deep learning methods for automated background phase error, velocity anti-aliasing, super resolution of for the flow data, and many other things. But I would really like to highlight one specific topic and one specific issue. So let me go back to one of the first slides of my presentation. And when I talk to some clinical people, they say, Sergio, the community have come with this amazing for the flow data, with this amazing for the flow sequence, but I really struggle to reformat all the data into the aorta, into the MPA, into the superior vena cava, inferior vena cava. It's really time-consuming, as Michael mentioned recently. So, and actually, I think people is right. We have come with these crazy methods to quantify 3D parameters for the flow, but still we haven't come out with a tool that allow us to easily quantify the standard measures in for the flow in a reasonably time. But I think maybe AI will come up with a solution for this, and I would like to highlight just two different words in the same area, which is automatic plane reformatting of for the flow. One paper just recently came out in 2021, in which they use a deep learning strategy using these 3D patches to find out what is the best plane that is aligned orthogonal to the aorta, to the MPA, to the superior and inferior vena cava. And as you can see here, the slices that the deep learning algorithm get are very similar to two experienced observers. We're also working on a similar strategy. In this case, we are developing a convolutional neural network that sequentially moves and rotates an initial plane towards a target plane, as you can see in this video. And the target plane, it could be any plane as you train in the network. So I think maybe these AI solutions might come available, and we can actually sort out the problem of measuring just the standard 2D measurements for the flow. So with that, I would like to conclude. So maybe in the near future, we will not only measure just 2D flow, but also maybe we will provide 3D full field quantification of several parameters. And as the previous speaker said, we might need still some clinical validation studies for some of those parameters to see whether it makes sense or not to put those parameters into the clinics. Although some of those parameters, I think they have been quite well validated as a wheelchair stress, and some people are already taking wheelchair stress into the clinic. But we are still lacking some software and standardization, and we are still lacking some software for an easy post-processing and less time-consuming post-processing tools. And maybe AI will come with some solution for this. As you see, AI might provide for the flow with high resolution, and the error corrections and segmentation might be done automatically. And we might have also some automatic software for reformatting and analysis. And with that, I would like to thank my collaborators in Chile and some other people in different places and who have provided me with some slides. Thank you very much.